Hello, and welcome to the tutorial on discount factors and spot interest rates. In the previous two tutorials, we used discount factors first to value bonds and loans, and then looked at how we could derive discount factors from the traded prices of bonds. But you may have noticed that we did all this without ever using interest rates directly to calculate the present value of future cash flows. So what we're going to do in this tutorial is make that connection, the connection between discount factors and interest rates. So what is this relationship? Let's look at an example. Suppose the discount factor for 10 years is 0.5. What interest rate I, compounded annually, will give exactly $1 in 10 years for 50 cents invested today? Well, we can actually do this using the TVM keys on our financial calculator. We would put 10 for 10 years in the N register. We would put 0.5 representing the present value in the PV register. Since there's no intermediate cash flows, we'd put 0 in payment, and then -1 representing the $1 in the future. And then to get the interest rate compounded annually that would equate all of these, we would hit the I key. And we do that, and we get 7.1773, and that, of course, means 7.1773%. So in other words, 50 cents invested today at 7.1773% per annum, compounded for 10 years, will end up worth exactly $1. So if we look at that in terms of the formula, it would be 50 cents times 1 plus the interest rate compounded for 10 years, that gets to $1. Or we could look at it period by period and say we start with 50 cents, we're earning this rate of interest on that, and gives us this balance, the rate times the beginning balance, and ending balance is the sum of the two. Then the next period, we earn interest on that higher beginning balance, and as you see, the interest starts going up. That's the compounding effect. When we add all this together, we end up with $1 in 10 years. Now, discount factors and interest rates each imply the other. So if we have the discount factor, we can get the interest rate, and if we have the interest rate, we can get the discount factor. So as previously shown, the discount factor for a given maturity, for example, for 0.5 for 10 years, implies the interest rate for that maturity would be 7.1773%. But if we had the interest rate, 7.1773%, and wanted to know the present value, we would do it this way. We would leave all of the registers the same, 10 N, 0 in payment, and -1 in future value. We would input 7.1773 back into the I register, and we would hit PV to compute, and we would get 0.5. So that leads us to the definition of the spot interest rate. The interest rate implied by the discount factor corresponding to the present value of $1 or 1 unit of any currency due at a single future point in time, for example, 10 years, for a given borrower is called the spot interest rate, or sometimes the spot discount rate, or sometimes when it's clear we're talking about interest rate, it's referred to just as the spot rate. So in our example where DF10 equals 0.5, 7.1773% is the 10-year spot rate. Using some algebra, we can derive the discount factor from the spot rate. So by definition, DFN dollars today invested at the rate RN for N periods compounded will get us to $1 in the future. So we can solve for DFN by doing a little rearranging. Divide both sides by 1 plus Rn to the N, and then you'll see here these cancel out, and that leads us with this equation. DFN equals 1 over 1 plus Rn to the nth power. Remember this formula. This is the key formula for discounting a single dollar at a future point in time at a single rate. Now, calculating the discount, we can calculate the discount factor directly from the formula. So if we did it using our numbers from our example, we would put in 0.071773 for Rn, 10 would be N, and we plug and chug, and we would get 0.5 for the discount factor for 10 years. We could also do this on our calculator using these keys. We would enter 1.071773, 1 plus the interest rate, hit enter, and that would show 1.0718, which is a rounded number. Then we would enter 10, which is how many periods we want to compound it for. Yx is going to do the compounding, and then 1 over x is going to basically take the inverse, as we show here in the formula, and that would give us our 0.5. So why don't you pause here and just make sure you can do this calculation, because we'll do this further on. Okay, so hopefully you got that. And I should point out, these give us exactly the same result as using the TVM keys. Now, note the spot discount rates for different maturities will typically be different. For example, the discount rate for 5 years will, well, the discount factor for 5 years will be based on the 5-year spot rate, which is not necessarily going to be the same. Now, if it were the same, if the 5-year spot rate were 7.1773%, the same as we use for the 10-year, we would put that in and we would change our n to 5, and we would hit PV and we would get this number, 0.7071. But what if the 5-year spot rate were something different? What if it were 6.2%? Well, we do the same thing, but we just put 6.2 in the I register. We hit PV again, and we get a different number, a higher number, 0.7402. So in general, the spot rates will be different for different maturities. And this defines what is called the spot rate curve, or sometimes the spot curve. And so in this table, you'll see the spot rates that we've assumed for years 1 through years 5. And using these spot rates, we can come up with a discount factor. So we already did the first one for year 5, where we assumed 6.20%, and we got 0.7402. And we could do it for the first year by putting 3.09 in the I register. And if we hit the PV key, then we'll get 0.97. We could continue to do that for 2, 3, 4, inputting each of these rates in for I. And if we do that, we'll get this. So 0.97, 0.92, 0.859, 0.7999, and then 0.7402 again. Now, the spot curve will be defined for short maturities as well, and these we could typically obtain from traded bills, short-dated bills. So for example, we may have rates for 1 month, 3 months, 6 months. Indeed, we'll probably have a rate even for 1 day overnight. And so we can fill out our curve using these spot rates. Now, the discount factors for less than 1 year maturities will reflect a fractional year of discounting. So we're going to use the same formula, but instead of putting a whole number in here as the period, we're going to use the fractional period. So for example, if we're doing this for 0.5 years and the rate, the annual rate compounded is 2.3%, we'll put that in here, but we'll compound it only for 0.5. And if we do that, we'll obtain this number here. And we can do that on our calculator using the same method we'd used before, but putting 0.5 instead of 10, for example. And we get this 0.9887. We can do that for each of the shorter maturities, and we'll get the discount factors for each of them. Now, the calculator's TVM keys can also handle fractional periods, and I just say be a little bit careful with how the settings are. The settings need to be set so that it does an annual compounding, but if that's done correctly, you can put in 0.5 for N, 2.3 for I, and you hit the PV key, and you'll get the same 0.9887 as we got using the formula and using the other keys to calculate it directly. Now, the spot rate curve will in general have a consistent pattern like one of these. Spot rates for close maturities will generally be close. The slope will tend to be consistently positive or negative, and it will tend to flatten. So we may see a normal curve like the gray one here. It could be upward sloping, but a little bit steeper. We can have a flat curve. We can have an inverted curve. And notice that close maturities tend to have similar rates going in kind of a similar pattern. And notice also that the curves will tend to flatten, and even more so as we go further out in maturity. So we can use this to estimate discount factors for intermediate points where we may not have a directly observable discount factor or spot rate. So for example, if this is our spot rate curve and we need to have a discount factor for a 1.5-year cash flow, well, what we could do is interpolate the spot rate and then use that. So step one would be to do that. So if it was exactly in between the 1 year and the 2 year, then the average of those two will be the interpolated rate. And in this case, it would be this number here. And then step two would be to use that rate in our formula and to obtain the discount factor using that interpolated rate. Now, I should give a caution here on compounding frequency. So we've been assuming in everything we've done in this tutorial that rates are being compounded annually. And that's very nice. It makes the math and the algebra much less tedious. You avoid the extra complication of compounding frequency. But it's worth noting that that isn't always the case. Sometimes compounding frequency is more frequent. And I should note it's just a matter of convention. And in some markets, for example, the US, the convention is to quote the rates on a semi-annual basis. So for example, if we were doing it on a semi-annual basis, we would have a different number quoted. So the semi-annual number might be 70529, and that would be the equivalent to 71773. And the reason for that is shown in this formula here. When the rates are being quoted semi-annually, what is assumed is you're getting half of the rate every 6 months. Every 6 months. And so you would calculate the formula for that by taking 1 plus that semi-annual rate, which would be the quoted rate here, divided by 2, and then squaring it. And that would equate to the annually compounded rate. So that's it on discount factors and spot rates. Let's just summarize the key findings. The discount factor for a given maturity implies a corresponding spot interest rate and vice versa. While spot rates for different maturities will in general be different, they will typically fall along a curve where nearby maturities will have spot rates close to one another. And we can take advantage of that curve and use intermediate spot rates, and corresponding discount factors can then be reasonably estimated using interpolation. So that's it for this tutorial. Thank you for listening.